Good morning, YouTubers. Got a special treat for you today. I was able to come out a bit early, get some drone footage. I know I teased that about, 11, 12 months ago. Got super busy. Wasn't able to actually get around to it. Today I was. It was pretty windy earlier when I was flying it, so it might be a little jumpy, but I hope you guys enjoy it. If you're new to the channel, welcome. I just talk about substation, kind of general education, what things do. If you're new, welcome. If you're not new, hopefully I cover something additional that you might not have learned before. I would say I know a fraction of what a lot of people do. The more I learn, the more I realize I don't know a whole lot. So there's always stuff to learn in these yards. This is a 138 to 34.5 substation. It's for a wind farm. As usual, we'll start at the high side, which is the 138 side, a low side obviously being the lower voltage. For safety purposes, you can see we have grounds hung. We've got the main switch locked out, and then we've got the breakers locked out on the low side to prevent any backfeed from the turbines. But that's actually kind of a misnomer. These new turbines need power to make power. So if I was to manually spin these wind turbines, it would not produce any power and flow it to the substation. It needs to sync with the existing grid. There are multiple disconnects and breakers inside of those systems. The computers have to be powered up, so there's no way that power can come from these turbines. But I know that the older turbines, that wasn't the case. Things that you have at home, like if you spin your alternator, it can backfeed power. These are not the case. However, just wanted to go over the safety for the low side and the high side. So again, we have the grounds. We've got our OPGW, which is that wire on top. That's a steel wire for protection from lightning and transient voltages. And also in the middle of it, it's got fibers. So those fibers come inside this box to where we splice it and transfer it into an underground non-conductive fiber, which runs into the control house. That gives us communication to and from the utility. Why I say to and from is because we're actually sharing data. We are able to share up to 500-600 different points of data within this yard with the utility. Also, they are able to remotely control our breakers if they ask us to do something and we aren't able to act in time. If they need to curtail us, which means they can shut us down from say 160 megawatts to 80, for example, if they have enough power on the grid, so they can tell us to kind of roll things back. Actually, how that happens, we haven't talked about that before. There's a server inside of this control room that talks to all of the wind turbines. It's made by the same turbine manufacturer. It's kind of the brain for the park. And you can tell that system, again, remotely or locally, hey, we need you to produce half the megawatts of the park. Say, again, it's 160, for example. You can say, hey, I want you to kick it down to 80. And through its systems, it will talk to the turbines and either run them back or just shut certain ones off. When I say run them back, it's because these turbines, the blades actually pitch on them to catch more or less wind. So it's not just one full speed. You can have them pitch to catch all the wind it can on like a low wind day. But if the wind is super high and it only needs to capture half of that fast wind blowing by, those blades will roll themselves back to catch less wind to maintain the optimum speed. So they will go full open to get to speed, and then they will curtail back to just keep that optimum megawatts. So it's a pretty neat system. So again, if they're asked to curtail, to shut down part of the park, to not produce as much power, which does happen from time to time, it'll either shut off the turbines or roll the blades back to get it to the desired megawatts. So that's a crazy system in itself. Tons of information and knowledge that I really don't know much about. So yeah, we share information with the utility, we share controls with the utility from this communication system. So we'll move to this switch. This is a double end brake switch. Double end brake meaning it brakes on both ends. This is a motor operated disconnect, MOD. It's motor operated, which is why it's called an MOD. Sometimes it can be hand crank. It's just kind of like a Cadillac option. If you're buying a car and you want certain seats, heated seats, you know, AC seats, you can do the same thing with these switches. You can add a motor operator. So this is operated remotely inside the control house or locally with these buttons. Or a third way, if let's say you lose power or something like that, you can take this handle off. This is actually a handle. Stick it in here and manually spin it. And how that works is through this linkage here. This is actually, well, they didn't lock it up correctly, but this cam right here is separated from this cam. And we have it lottoed right now, which means if anybody was to operate this somehow, either through the button or manually or inside the control house, it will spin, but this won't. That's what we call a lockout in this case. We have a physical lock on it, even though this wasn't quite done right. You're supposed to run it through the gold and not the pin. This physically disconnects it. When it is in place and this lotto is out, this arm here will fit inside the cam, just basically like a key, and it will operate as normal. You've got your open and your closed, so as this thing rotates, you'll see the closed, and it operates through the linkage up on top, and they all connect together. They all move, all three poles move as one. What else on these? The contacts up there, so you can see those kind of gold spring looking things. That is where the this center kind of conductor pole will spin, and it will roll into it. So it will spin diagonal, and then it will roll that flat bar, that bar that you see there, it will roll it so it seats in those fingers. Typically, the more amps that a switch sees, there will be more fingers to give more contact, and those fingers have a spring inside of them, so they can kind of flex when those jaws rotate in. So there's 8 springs in there. You see the four brackets on top and on bottom. Again, they'll add and subtract those based on the amperage. So it's very important to time this correctly. You want it to fully close and fully roll in to make contact. If it doesn't roll in all of the way, it will not make contact or good enough contact, and eventually could burn up. This is doesn't say the amperage on it, but I want to say it's 1200 amps just because that's kind of what the standard is for these high voltage switches. Many different kinds of switches. This is just one of the many. Moving on to these CCVTs. There are CCVTs, CVTs, and PTs. CCVT stands for capacitive coupled voltage transformer. The CVT is just a capacitive voltage transformer, like there's only one capacitor instead of many in series. And then PT, which is just a potential transformer with a winding inside. I don't know what these are off the top of my head. I haven't looked at the nameplate. CCVTs or CVTs for sure. It's definitely not a PT. And using the capacitors is just a more efficient way to get the voltage from the primary down to the secondary. So what do these things do? They take a ratio of the primary voltage and it transforms it into a manageable voltage, which in this case, I think these are 2 windings, so it should be 120 volts and 67 volts. So it just brings it down to a manageable voltage so we can bring it into the control house. Obviously, you can't bring 138,000 volts into the control house. So again, when I was saying that this is a ratio, that means that if you have the perfect voltage on top, 138 kV, you're going to have exactly 67 and 120 volts down below. If you have half of that on the primary, then you're going to reflect half of that on the bottom. It's just a ratio of whatever the primary voltage is. So again, we have 3 of them, 1 for each phase. You've got to have all 3 in order for the system to really be protected. You want to protect each phase and see what's going on at each phase. So we wire it in at the top, it goes through this conduit. Again, and the other 2 actually go into the ground and then over into this junction box. I didn't preface that we're going to energize this in a few days. There's still a couple things we need to do. But yeah, most people are surprised at the number of wires that we have in here. We take, again, the 2 different windings from each of the phases. We have fuses that we'll install here for protection. We leave them out when we do the first energization. And why we do that is if something was wrong with these units and it had an odd voltage or way high of a voltage, we don't necessarily want to send it inside where we have people and we have equipment. So what we'll do is we'll take our measurements here with our FR clothing and verify that the voltages are nominal. Then we will install the fuses, and that will give power inside. A lot of wiring here. One thing I really don't like are these sticky backs. You guys have probably used them before. We haven't even energized the substation yet, and they're already coming off. These sticky backs are terrible. You always want to run a screw into the middle of the sticky back to actually hold it. The sticky just is not sticky. They should call them not sticky backs, because they're really not. So that's the low voltage cabinet here on the CCVTs. We'll give this kind of a quick cleanup before we go. Also, before we energize, we check the continuity of all the fuses just to make sure that the fuses are good. We don't want to install a fuse thinking that everything's fine and get some odd readings. We just want to eliminate any issues before we energize. Moving on to this breaker, it's a 138 breaker. SF6 is the gas. That is the gas insulator, sulfur hexafluoride. This is no different than a breaker in your house. It's just bigger and uses insulating gas. You don't need insulating gas for only 120 volts. So, you can go to Home Depot and buy a breaker for your house. It really kind of does the same thing. It's just open or close. That's it. It's a dumb device. It's not smart. It simply gets its commands from the relay inside or the push buttons inside, the open close, and it does what it's told. That's about it. You can see at the bottom that they've got these kind of pretty little silver covers. Those are actually holding or covering up the CTs, the current transformers. Those are on both sides and on all 3 poles. You can get these with just one CT or even no CTs or many CTs. You order the amount you want. You can also order the type you want. If you want like revenue quality CTs, which are more precise but more expensive. But there's a number of CTs underneath there, and then the secondary wires you can see come out and all run inside the control box. So the 2 things that you need in order to protect your system are CTs, which there are many in here, but in the substation yard, but there are some here, and you need PTs. And here's your PT. So you can watch your voltage with these over here, the CCVTs or the CVTs. And you've got your current that you can watch here. There's also some of the transformer that we'll get to. So with those 2 things, you can protect your system. We'll just take a brief look in the control box. I was saying that this is not quite done, but you've got some push buttons here locally. So you've got local or remote. So if you're working on it or you need to lotto it out and you don't want anybody to remotely be able to close it, you can set it to local. So you've got the CT wires on that side. I'm not going to open up this cabinet. And you've got a lot of other wiring as well. Here's some of the mechanical linkage in the springs, things like that. This will open or close. A rod that's inside is kind of a current carrying rod. Close this. And that rod is in the middle of this tube. And there's an actuator on this side that will either ram it shut to touch the other part of the steel tube, or it's not really a tube, it's a solid bar, or it will open it. And that's what the physical springs and linkage does. So these are all linked together through the top, which I can't reach up there to show you, but they're all linked together. There it is, there's the bar. And then you actually can see a counter there, open, or not a counter, but indicator, open and close indicator. So it's showing open. And that bar runs all the way across. They will all do the same thing. So just the breaker, just open and close. There's that SF6 gas inside that acts as the insulator. If you didn't have SF6 and it was an oil-filled breaker, it would be pretty dang big, really expensive, really heavy. This gas is great. Makes things much less expensive. And there's actually a new gas coming out. They're saying that this gas causes like ozone issues. It damages the ozone, but I don't understand that because this gas is heavier than the air, so it doesn't release and go up like helium. It falls down. So I'm not sure how this is affecting the ozone, but I'm not the expert. So there's a new gas coming out. I'll link it below. It's pretty interesting stuff. Apparently it's not very, or it doesn't harm the environment, but it's a very new gas. I think there's only one company, maybe two, that even have one in service. I was coincidentally on an airplane with a manufacturer for breakers, and they were just putting their first 138 breaker in service with that new gas. So to be determined on that new stuff. Next, we'll move over to the transformer. This is really the heart of the substation. It converts the high side voltage, 138 kV, to the low side voltage, which is 34.5. It converts it through the windings and the iron core of the transformer. I think these have a tertiary winding too on them. I don't know too much about what the tertiary winding does, other than I know that it helps with the eddy current and helps with its efficiency, the efficiency of the transformer. So you've got all these crazy fins on the side. This is just for cooling. You can see that you can just look right through them. So each one of these little veins has oil running through it. Also have fans down below. So this is how the transformer cools itself. If you didn't have these fins and didn't have the fans, you wouldn't be able to produce, or to convert that much power. Let's see if I can find the nameplate on this guy. Here it is. So it's a 138 kV to 34.5 kV. Sometimes it takes me a minute to find all the information. Okay, so it's 134 MVA. Oh, okay, no, it's 134 with just the oil and no fans, and then it'll do 179 with stage 1 fans, and then 224 MVA with stage 2 fans. So you can see how much more power this transformer can convert when it is able to more efficiently cool itself. If you put 224 MVA through this thing without any fans, it would certainly overheat. So fans make a huge difference. Proper cooling really is what makes the difference. So this does have a tap changer on it. You can see that there's a number of CTs in this transformer, which we'll talk about when we go on top. This is so it's a Y with the grounded neutral on the secondary, and it's also a Y, or on the primary, and then it also is a Y on the secondary with the grounded HO, and then we've got that tertiary winding that we were talking about earlier that I don't have a whole lot of knowledge on, but it just helps with the efficiency. Usually I see a delta Y, so delta on the high side, but anyway, there we go. So we can talk a little bit about kind of protection of these things. So this is obviously in a very expensive unit. I mean, this is millions of dollars for this. It's the heart of the substation. You don't want anything to happen to this. So there's a lot of things that they have installed to protect it. You've got this temperature gauge here. It will tell you the liquid temperature. And then you see a number of metal screws with little pointers on the top there. Those are different alarms. So when the needle hits, also the red is how hot it has gotten. So that will always move to the top. But when we energize this, I like to reset it so I can track that. So anyway, the first metal piece is most likely going to be your stage 1 fan. So at roughly, what is that, 55 degrees or 60 degrees, it will kick on the first stage of fans. Then the second one, you can probably guess, it looks like 75 degrees or something, maybe 65 degrees, that's going to be your second stage fans. As you continue on to the third one, it looks like 85 C, and that's C, not Fahrenheit. That is going to probably be your high temperature alarm. And then the last one, which is set around, 105 C, that's going to be your trip. So it's going to say, hey, I'm way too hot, I'm not getting any cooler like I should be, Both stages of fans should be running. I'm still continuing to overheat, so trip me offline. So that will send a signal through these wires, which go inside this control cabinet to the relays that say, hey, trip me. So that's just one of the many alarms. Move on to the fans we talked about. And this device here, this is a pretty cool device. So just like if you take blood tests, you can learn a lot about yourself and your current health by your blood. This does the same thing, but with the oil. It will cycle oil inside of itself, and it'll take a reading roughly every 2 hours and log that data and send that data through the SCADA system into the control house. And it will give all sorts of information, the types of gas that it's seeing, the condition of the oil, the moisture content, everything like that. And then you can program this or inside to say, hey, if these values hit X, then we want you to send an alarm. Or if these values hit X, we want you to trip the transformer. That is what this thing does. It gathers data from the transformer, oil, and it will send that inside for the system to do whatever it needs to do with that information. This piece here is a pretty important piece. It's not required. It's very expensive, but it's an OLTC, an on-load tap changer. So this has physical linkage inside that pipe, which run inside the transformer, and it will physically change the ratio via the windings to always keep 35 kV on this side of the transformer. Why do you want that? Well, these turbines are pretty picky. They like a nice consistent voltage, and the primary will usually fluctuate through the day. Not huge swings, but it will raise and lower, and it might be 142,000 volts, or it could be 130,000 volts. Whatever that fluctuation is, this device under load will change the ratio of the transformer in order to maintain a 35 kV on the low side. And again, this is an OLTC, and then there's LTCs. The OLTC is an on-load tap changer, and LTC is just a load tap changer. Huge difference between the two. If you operate just an LTC under load, it will most likely literally blow up on you. You're not supposed to do that. It's very bad. But this one allows you to change it while it's under load. And you can kind of see the ratio there. You've got the N, which is its a kind of natural point of transformation, and then it will either raise or lower, raise 16 or lower 16, and those are just the different steps in order to maintain your consistent voltage on this side. So this is probably, I don't know, a $250,000, $300,000 adder for this, but it makes your system much more reliable and efficient, and keeps things running. So that's the OLTC. And we're talking about protection again, or different alarms. So this system is another form of protection. It monitors the oil. If things don't look good, it will tell the appropriate device to, hey, you need to trip. This here is a PRD, this is a rapid pressure release device. So if you have some sort of big explosion inside and you have that pressure wave, it will hit this, there's like an air bladder inside here, and that will open up an alarm contact through this wire, and it will send a signal inside to, hey, trip me off because I just had some kind of explosion inside me. So we'll move on to the low side, coming out from the transformer. The first device we have here is the neutral grounding reactor. I know we've talked about this before, but this essentially will soften the blow of any fault current to ground. So if you have a fault in the field on the wind turbines or something like that, all that fault current will come back to the neutral of your transformer. And this device basically kind of softens that blow to ground, so there isn't as much of fault current hitting your system. It's sort of like an airbag, except this is reusable. It doesn't pop. It just keeps working. So that's tied to the XO. And noticed again, just kind of from my last video with another yard, it's supposed to run straight from the XO to the reactor, then to ground. In this case, the wind turbine, or excuse me, the main power transformer commissioning crew installed their ground on there. We actually need to go take that off because right now it's bypassing the NGR, and we need to take that off. The people that come put the transformer together, you always want to have your neutrals grounded, typically, and they don't really care what happens outside of this yard, so they didn't even probably know that we had a neutral grounding reactor. So it's just one of those things where it was kind of a scope gap. You know, they just did what they were supposed to do. We also did what we were supposed to do, but we actually need to go take that strap off. So all of the neutral current will run through this NGR. You notice the secondary wire here, how it runs into the ground. Like, why is this different? It's a really huge wire. This is actually 35 kV insulated cable. The reason that we have this insulated cable is if there was a ground fault condition and somebody was just hanging around in this area, you would have a voltage on this wire during that fault event, and it could jump to you and then kill you. So they insulate this wire, so during that, you know, fraction of a second event, that voltage will be contained within the insulation and not to you. And then there's a connection to the ground grid that's accessible here with this box. So sometimes they use 35 kV insulation, sometimes they use a 600 volt insulation, sometimes they don't even insulate it. It's just I prefer this way. This is kind of like the maximum insulation level that you would need, keep you safe. But you know, how many times would you have a fault current event and have somebody standing here? Probably 1 in 10 million, but you never know. So that's the NGR. The next thing in line is the transformer. This is a station service transformer, meaning this is giving your station electrical service. So we're tapping it off one of the phases on top. One of the phases of 34.5, if you do the math, is 19,900 volts. It runs through the fuse disconnect there. It's currently open. We close that with a hot stick. That will give primary power to the transformer, and then it will convert the 19.9 to 120 and 240 volts. We also have a utility backup. You can actually see the transformer over there outside the fence, the green transformer. We like to use this as our primary because it's sort of free. I mean, the wind farm's producing the power. You don't necessarily have to pay somebody for it. It's cheaper just to use your own power than it would be to purchase it. You know, at the end of the day, what are we talking a month? Maybe like, you know, $500 or $600 maybe, or maybe $1,000 at the most that you'd pay the utility. But either way, just take it from your own system. You don't really have to pay that invoice every month. And if there is an issue, then you can use that backup. And that's how we're running right now, is on the backup, since we haven't officially energized this yard. So the station service transformer. Next is the low side switch. I'm going to switch to regular angle. This low side switch physically disconnects the 35 kV voltage from the bus that you see here. And this bus basically just spreads out the voltage so you can have different breakers hooked up to it. So this has fingers as well, like the other one. These are a little bit bigger fingers, but it's very important that when this switch closes, that it closes and it rolls. You have to have it roll and grab all those fingers. If it doesn't roll and grab those fingers, you will burn it up. Absolutely, and these are kind of notorious for burning up just because there's so much more amperage on the low side than there is on the high side. I think this is like a 3,000 or 4,000 amp switch. In comparison, the one on the high side, that's only a 1,200 amp switch, and obviously it's because the higher the voltage, the lower the amperage, right? So this is a lower voltage, you're gonna have a lot more amperage. Next, you have the PTs. So we talked about CCVTs, CVTs, and PTs. These are potential transformers. You notice they're a lot they're a lot smaller than the other one. Well, that's because the ratio isn't as high to get to your 120 volts and 67 volts. And so the core, like the windings, don't have to be as long. You don't have to have as many winds to get the voltage down. So this is, I think, a 175 and 300 to 1 if you do the math on it, which I'll put down below. So this protects your low side. It brings the voltage down to a manageable voltage, which is 67 volts and 120 volts. Open this guy up. And so those wires that come from those 3 PTs, see the 3 sets of wires, those are coming down into the terminal cabinet. Again, these are fused for protection because we don't want to burn up the PTs or overload the PTs. That transformer there, that's meant to push some amperage. It's, you know, roughly 400 amps. These little ones here, they're not made to really produce a lot of current. It's just there, just touching the wire and giving you a voltage that you can bring inside the control house to monitor your voltage on your low side. So that's why they're not big compared to that bad boy there. And I think we put 5 amp fuses in these, which, here's one. Okay, 15 amp. I'll go check the prints. There you go. It's just an amperage fuse in order to protect your PTs from melting. So we'll do a little bit of cleanup in this, kind of vacuuming, but no sticky backs. That's good news. Next we have the hook stick switches. We call them hook stick switches because they are closed with a hook stick. You can get these like single poles like these are. You can close one at a time. You can also get a MOD, which is like a motor operated disconnect that we saw on the high side, or you can just get a hand crank disconnect that closes 3 phases in at once. It's just one of the cheaper options than going with like a 3-phase switch. There's nothing wrong with these. A lot of people think that you have to have all 3 phases closed in at the same time. You really don't, as long as you're not like utilizing it. All this is doing is sending power to this breaker, which is just either an open or a closed, and it's just conductor, right, that you're energizing. So you can certainly close one of them at a time. It's no big deal. You close it. You want to make sure that the jaws close, and you fully seat these switches when you slam them shut. But once you're slammed in shut, you're good. You just go to the next one, and get them slammed in. So this is a cheaper option than going with a 3-phase system. I think these are good for 600 amps each. Actually, it's probably more like 1200 amps. But anyway, I'll put it down below what the nameplate is. So that feeds down to these breakers here. You can see that we have some avian protection. So it's basically insulation that we have on top here. So if a bird lands on top of the breaker and spreads its wings, it won't, not only will it not die, but it won't trip the system, which that's money, right? If all your turbines are producing power and then you trip offline because of a bird, that's going to be pretty costly. Well, we call them nuisance trips because it tripped to something that wasn't necessarily like a problem. Like if you have a branch that touches your line and trips it out, right, that would be considered a nuisance trip. So of course you don't want to kill birds either. But so anyway, these hook stick switches come down and feed this breaker. This breaker's different than the high side because there is no SF6 insulation. It's all kind of air insulated inside. They're just separated inside physically with an air gap. The only thing that does have vacuum on it is the actual bottles that open and close. And when you hit the button, these vacuum bottles will open or close, and they have a vacuum in there to eliminate as much arcing as possible. So this does not have any gas in it because it's not needed. This is also a grounding breaker. So what that means is when it opens, it actually opens to a grounded position on the field side. Oh, good note. So this breaker does not have the grounding option on the bottom because this is feeding the capacitor banks, and you don't need to actually ground the capacitor banks. Here is one here for the wind turbines. And you can see how the nameplate is different it's showing an open and a ground, because when it opens, it grounds itself through here, which means that field side, those field side conductors are grounded. And again, in comparison to this one, this is a non-grounding breaker. There's no ground shown on it. It's just an open. And that goes to the capacitor banks that we'll talk about next. So we'll switch to the other side. We'll take a look. I think we still have a little bit of work to do in these. A lot of work to do in this still, just of cleanup, things like that. We had some wiring and some drawing issues. But we have AC and DC that come into here. The AC powers your heaters, powers your lights. Your DC powers your springs for your trip coils. This particular version has 2 trip coils, TCS1, TCS2. Those are your different trip coils, and those will be lit up when each of those coils has power. You should always have 2 lights on because it's redundant. If you have a 1 trip coil that goes bad, you may not be able to trip out the breaker if it needs to. If you had that problem, then instead of this breaker tripping and closing down just 1 circuit, the next thing in line to open would be the high side breaker, and then you would lose all of your other breakers, right? So that's why they have a redundancy in here. They have 2 different trip coils to make sure that if there's a problem, this thing will properly trip. So the DC powers those coils. It powers the motor that charges the spring, and the DC also runs through the different normally open, normally closed contacts. Like the other breaker that we talked about with the CTs, these also have CTs, but they're on the inside of this breaker, right underneath the case. So there's a number of CTs in these. Again, you've got the combination of the voltage through the PTs, and then your current with the CTs. That gives you proper protection. So each of these will be able to protect itself individually. That way you don't lose everything in case you have an issue with just one. So these are just mirrors of each other. Really, the wiring's exactly the same. We also have hook stick switches on the turbine side. So if we want to isolate the turbines from the electricity, we would open the breaker, and then we would also open the hook switches. You could actually still have power going to your breaker, but it obviously stops in the middle with the vacuum breakers. So you'd have this open, you'd lock it out, and on these hook stick switches, you'd hang a tag. Running over to the riser terminations. So these are coming from the field. You also have lightning arresters up there. Kind of we talked about, you want to protect your system from any lightning strikes. We've got them on the high side, and we have them on all of the low side risers. Again, that's to protect the station equipment from any damage as a result of a lightning strike, or what we call funny, or the cool name is transient overvoltage, which is something transient, which would basically be lightning. So protecting you from a lightning strike. We've also got these feeders grounded for added protection. I actually didn't know we had these grounded, but glad we do. You don't need grounding if you don't have any people working on them. We are all done with these. They've been signed off, completion cert's done, so we can actually remove these anytime we want because we don't have anybody physically working on it, but we'll leave them on for now. What's different about this one? Oh, okay, so these are just single risers. So it's coming from the field. All the wind turbine power is running into these cables, and it goes up and over into this breaker. So you have one breaker controlling one circuit. This one's a little bit different. You've got 2 sets of cables running to the wind turbines. So it technically is still one circuit because you're tied to one breaker. But it might have just been an issue with probably cost savings on the cable. We'll run one circuit out and hit a few turbines, and then we'll run another circuit out, maybe the other direction and hit the other turbines. So they most likely did it this way in order to save money on the overall length of the cable. So because this has 2 2 sets of cables on it, you've got your hook stick switches over here. You notice that this one doesn't have it on the other side like these. It's because we need to have 2 sets. So they ran it over to this structure just for itself. You've got 3 hook stick switches on this side, and then 3 hook stick switches on the other. Again, each set has its own lightning arrestor, and then that runs into the ground. which goes out into the field. This looks like, what size is probably this? I'm trying to find it on here. Here we go. It's back, it's upside down, but it's 750 kc mil, 35 kV, 100% insulation. 100% insulation equals 345 mils thick, and this is a XLPE. I have another video that talks about this underground cable. It's pretty amazing stuff. So I think we pretty much hit everything. All these circuits run out into the field. We have our lightning protection. So we have these, what we call static poles. That's to protect the equipment from lightning. And then you've got the wires that run across to the other one. So it really kind of forms a shield and protects all the physical equipment. Well, I got a little busy, so I had to pick this up later. I didn't catch the capacitor bank yet. Just wanted to talk about that. Capacitor banks are here for power correction, and what that means is, like, when the voltage, when you have a sine wave for your voltage, your sine wave for your current should be exactly the same, up and down. As these turbines ramp up and ramp down, sometimes the current can shift away from the voltage sine wave and can either lead or lag that voltage. When that happens, you have a lot of inefficiency. That difference in your sine wave is wasted power, and these capacitors will help realign that current and voltage sine wave to a power factor that's zero, or basically it's zero. And we're allowed to be within 0.95 lead and 0.95 lag with the utility. So there's a lot of studies that go into how many capacitors you need. Capacitors will fix the current and realign it one direction, but not the other direction. If you want to align it the other direction, you need reactors. Those will help kind of do the opposite of what the capacitors do. So there's a lot of factors that go into determining if you need capacitors, if you need reactors, and if so, how much. The turbines are a big part of it. The utility is a big part of it. So every substation is different. In this particular substation, we just need capacitor banks. And we don't really need that many. There's actually a total of 4 capacitors for each phase. And there's 2 banks for a total of 8 capacitors. So it's not a whole lot, but it's what was needed to maintain the minimum standards set by the utility. This is a little bit different here. You don't see these all the time. They're harmonic filters. They're essentially reactors, but they're built in such a way to eliminate harmonics, because a lot of times these capacitors will create harmonics that are bad, and so we need to add these harmonic filters in there to eliminate those bad harmonic steps. So sometimes you see them, sometimes you don't, and again, it's just part of the design. This is kind of a neat design, how they stack them on top of each other. It saves on your foundation work, so you have one foundation instead of many, but it's pretty cool. So that's really the capacitors in a nutshell. Capacitor banks, and then your harmonic filters, and then your circuit switchers. Circuit switchers are really just a breaker. It's just an open and close. That's all it does. It's just a different type of design. It's made for just many more repetitions than the other standard breakers, and a lot more goes into it. These all open at the 0 point of your sine wave. So technically they're separated by milliseconds when they open, but they open on the 0 point to basically help with the arcing on the actual contacts. If you open on the 0 point, there's technically 0 voltage there for that 1/60th of a second on each of those phases. So pretty neat system. It is SF6 insulated, so it can be this size as compared to the air insulated breaker right here. So I think about it, guys. I hope you liked this video with the drone and a little bit of GoPro footage. I hope you learned something new, and make sure to stay safe and take care of each other. Thanks.